Okay, hello everybody. Today we're going to talk about lesson number 7. So this is still section 1.6. We're going to talk a little bit more about piecewise functions and about the greatest integer function in particular. It's possible that everything in this PowerPoint again is review, although some of it you probably do need a refresher on. So let's go ahead and get started. Remember that the previous PowerPoint was all about just reminding you about the different parent functions and what they look like. And now we're going to hone in a little bit more on piecewise functions. So a piecewise function is basically a function in pieces. It has to have 2 or more functions. We'll usually have 2 or 3, although it certainly could be more. It'll have some name, f of x, y equals, whatever the case may be. And then you'll have the different pieces that are defined over the different domains. So the first piece of this piecewise function is 3 plus x. That is, of course, a linear function. And that is only going to be true for the domain x is less than 0. Then you have the second part of your function here, that's part of a quadratic, and that's only going to be true when x is greater than or equal to 0. For most piecewise functions, the domain is going to be all real numbers, meaning that wherever the first one stops, generally the second one picks up. It doesn't have to be that way, but again, it certainly is the majority of the time. So if you take a look here at the picture, you're basically going to take each function and graph it separately. When it comes to graphing 3 plus x for x is less than 0, when x is less than 0, you can't just start at the closest integer, such as -1. You have to account for all the values between -1 and 0, of which there are infinitely many. So even though you technically can't plug in 0 because it's not defined, you have to know where the function would exist so that you can draw it as an open circle. So here's the open circle here. If you were to plug 0 into that linear function, you would get 3. So 0, 3 is where you're going to have an open circle. And then either just graphing based on how you know a linear function should look, it has a slope of 1, so you would go down 1, left 1. You could also then choose some values that were less than 0, things like -1, -2, -3. Basically plot a couple of points until ultimately you get half of your function looking like such. Then to graph the second piece of the function, x squared plus 1, 0 is included. So you're going to go ahead and plug 0 into that equation. If you square it and then add 1, you're going to get 1. Because of the fact that it's included, that's going to be the closed circle. And then ultimately here is your final answer. When it comes to piecewise functions, again, generally, as I mentioned, the domain is all real numbers. The range is typically something that we do want to consider. So if you take a look at this function in particular, the blue function goes all the way down to -infinity. Then there's a little bit of overlap. The red function goes all the way up to +infinity. So the range of this piecewise function is all real numbers. Again, I could ask you for the domain as well, but most of the time the domain is automatically all real numbers. So usually the range is a little bit of a better question. Evaluating a piecewise function, I'm pretty sure this goes without saying, but takes me 30 seconds to mention it, so I will. If you're trying to evaluate a piecewise function for specific values, you only are allowed to plug those values into the appropriate piece. So here in this example, you have 2 pieces, one for all the things that are greater than or equal to 0, and one for all the things that are less than 0. In question A, if I'm asking you for f of -3, you're only going to plug it into the piece of the function for which it is defined. So -3 is less than 0, which means you would only plug it into the first piece of the function. For B, f of 0, that would be in the second piece of the function. And then f of 4 would also be in the second piece of the function. So again, pretty straightforward, but just in case, never hurts to have a quick reminder. Here are several more functions that are already done for you, just so you can kind of get an idea of what they look like. And again, I kind of choose these graphs from the internet. So technically there should be arrows on the ends here. You should add them in when you're graphing for yourself. But for now, just go ahead and take my word for it that they're there. So the function on the left, there are 3 different pieces. The piece to the very left, that is a linear with a y-intercept of 2 and a slope of +1. The piece in the middle is a constant function at 1. Notice that at the left bound, it's a closed circle, whereas at the right bound, it's an open circle, and then you have the third linear piece over there to the right. Please make sure that you note that when you are graphing any and all piecewise functions, they must be functions, which means they have to pass the vertical line test. You can never have 2 closed circles on top of each other. You could have 2 open circles, even though that's pretty rare, but you can never ever have 2 closed circles because unfortunately that would mean that it's not a function. Over here on the right side, the left part of the function, that's a linear equation with a slope of 1. The right side of the equation is a linear function with a slope of 2. Again, in these two cases, the pieces don't happen to meet, but they certainly can. So whether the function pieces meet or not matters not. If they do happen to meet, so if you essentially have an open circle on top of a closed circle, you just draw it as a closed circle, and I will assume that you know that that's where they meet. Two more examples. The one on the right, a little bit more complicated since you have a couple of pieces of quadratics there. Again, there are arrows on the ends here. If you wanted to talk about how you would create these from scratch, just like we did the first couple of examples, you would plug some values from this domain into function number 1. That would give you piece number 1. Plug some values in from domain number 2, that would give you piece number 2, and then ultimately piece number 3. And again, even if the value technically isn't included, you do have to plug it in so that you know where the open circle occurs. There are ways to do piecewise functions on the graphing calculator, although they are a little bit complicated. So my advice would be to just kind of do it old school by hand. Speaking of by hand, let's go ahead and do a couple of these together. So I'll start us off with a nice easy one here. Piecewise function of two pieces, one for x is less than 0 and one for x is greater than or equal to 0. Depending on your comfort level, really will decide how much work you have to do here. When in doubt, you can feel free to go ahead and make a table. So like, let's say that I wanted to graph 2x plus 3 for x is less than 0. Again, technically I can't plug in 0, but I do want to know where the open circle is. Then pick some values that are in fact less than 0, like -1 and -2. Plug them in, you get values of 3, 1, and -1, respectively. So at 0, 3, you are going to have an open circle. Then -1, 1 is a point, -2, -1 is a point. The slope is just down 2, left 1, down 2, left 1, down 2, left 1. Basically, you just need a couple of points to show what the graph looks like. And again, it's a little bit hard for me to graph with my stylus, so yours should look even better than mine. Then for our second piece, let me go ahead and change the color here just to switch things up. So 5 minus x for x is greater than or equal to 0. So again, if you need a table, make one. If not, do it mental math. If you plug in 0, you get the point 0.05, and that is a closed circle. Then you have a slope of -1. So you would go down 1, right 1, down 1, right 1, down 1, right 1 a couple of times. Probably good to get all the way to the x-intercept. Go ahead and graph it, and that is in fact your piecewise function. So from here, again, the domain almost always for piecewise functions is all real numbers. Let's talk about the range. So for the range, the highest value that is reached by either function is 5. Because it's a closed circle, we're going to use a bracket. And then because it goes down, 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 we're going to say that the range is -infinity to 5. And we're going to use a bracket on the 5. Again, you should always be using interval notation, and your infinities, positive or negative, always get parentheses. Let's go ahead and try number 2, and then notice this little qualifier here, be able to work backwards. That means that if I were to give you a graph of a piecewise function, you should be able to work backwards and write me the equation. In order to do that, you would have to be able to identify what the various intervals were, and then you would have to be able to tell me the equation of that piece of the function. Yes, there is a very good chance I will ask you to do that, but if I do ask you to do that, it will probably be a relatively straightforward, more likely 2 pieces than 3, although I guess it could be, but please make sure that you also could work backwards. All right, so 4 minus x squared for x is less than -2. So again, if I were to actually plug in -2, I would get a value of 0, but that would be an open circle. Let's say that I plugged in another value that was less than -2, like -3. If I were to plug that value in, I would get the point -3, -5, and then I could go ahead and generally sketch that piece. It's part of an upside down quadratic, so just make sure that it looks curvy. Let me change the color again here. So for the piece in the middle, 6 plus x, that's a linear function, and that's going to go from -2 to 0. So if you go ahead and plug in -2, you're going to get a value of 4, and that is going to be a closed circle. Then you have a slope of 1, so up 1 over 1, up 1 over 1. By the time you get to 6, you're going to have to make sure that you make that into an open circle. And again, my graph is never going to be perfect on the computer with the stylus, but yours should be better than mine in real life. Then finally, one final piece, so the square root of x plus 3. If you go ahead and plug in 0, you get the square root of 3. The square root of 3 is 1.73. That's a closed circle here at 1.73. And again, it does not matter that it's a decimal. That's perfectly fine. Then you could choose any value greater than 0, probably a good idea to try to pick the nice ones. So what I mean by that is if you plug in 1, you get the square root of 4, which is 2. That's another point on this graph. Then try to look for another good perfect square. So let's say you plugged in 6. If you plugged in 6, you get the square root of 9, which is 3. Again, decimals are perfectly fine, but if you want to make it easier, go ahead and look for those nice numbers. And again, that should look like part of the scoop since that is a radical function there. So here we go, passes the vertical line test for sure. The domain, all real numbers. Let's consider the range. So if you take a look at the range, the lowest that it goes, look at the red piece, goes all the way down to negative infinity. Then it gets bigger and bigger and bigger. Then it clearly stops once you hit the x-axis, and it stops on the x-axis at 0, which is open, so use a parenthesis. Then it picks up again on the green graph at the square root of 3 and then continues to just get bigger and bigger and bigger and bigger. Remember, even though this piece, of the function is rising relatively slowly, it's still going to just get bigger and bigger and bigger all the way to infinity. So to finish this off, starting at the square root of 3 and then all the way up to infinity. So the next parent function is called a step function, and it's the greatest integer function in particular. So they call it a step function, surprise, because it looks like a set of steps. Just make sure you know a new vocab word. As you go from one step to the next, you do that by jumping. So that's a word that's used in calculus. A jump is where you have to essentially jump or move from one of the steps to the next, or just basically from one piece of the graph to the next. So that is called a jump. The greatest integer function in particular, again, you probably have seen it, although maybe not recently. So the greatest integer function can either be denoted with double brackets on both sides or single brackets on both sides. I've seen both. I don't care which one you use, but just make sure you know that both are options. So here is the definition of the greatest integer function. For whatever value of x you plug in, you are always going to get out the greatest integer less than or equal to that number. So a couple of calculations over here. If you were to plug in -1, the greatest integer less than or equal to -1 would still be -1. If you were to plug in -0.5, you would go down to the closest integer, which would be -1. If you were to plug in 1/10, which is 0.1, the greatest integer less than or equal to 0.1 is 0. 1.6 goes down to 1, 2.3 goes down to 2, -3.8 goes down to -4. Always be careful with those negatives because the closest integer will always be going down, which is less than. Because of the fact that there are infinitely many values that have an integer y value of 1 or 2 or 3, that's exactly why it looks like a set of steps. So consider this first step right here. If you plug 0 in, you get 0 out. If you plug in 0.1, you get 0. 0.5, you get 0. All the way up to 0.99999. Once you actually plug in 1, boom, you jump to the next step. 1.5, 1.7, 1.999, you stay on that step. Once you plug in 2, boom, jump to the next step. So you can't just leave the step unfinished, which is why you close it off with an open circle. And then a similar thing happens as you plug in the negative. And again, because the closest integer will always be less than, that's why the stairs are going down. Again, this is called the parent function. So lots of different changes can occur, but generally speaking, there is a 1 unit from left to right and a 1 unit jump from bottom to top between the stairs. You can obviously add some transformations into this. So for example, let's say that I was to say that f of x was equal to 5 times the greatest integer function. And again, double brackets or single brackets, it really doesn't matter. Let's say that I wanted to find f of 6.5. That would be 5 times the greatest integer function of 6.5. So 6.5 would go down to 6. 6 times 5 would give you an answer of 30. So even if there are other values in your equation, always do the greatest integer part of it first. Just like back in the other parent function video, here's a couple of things that are always true before you start moving around and stretching and shrinking. So the domain is all real numbers. You can put in any value of x that you want, but then the range is kind of interesting. You're only ever going to get back the integers. There is no interval notation way to say integers, so you just go ahead and say integers. There is a single y-intercept here at 0, 0, and then there are actually infinitely many x-intercepts. It's basically anybody that lives on that step. The graph is constant between each pair of consecutive integers. So it's constant from 0 to 1, constant from 1 to 2. Obviously, we're not going to write all of those out, so we say that it's constant between pairs of consecutive integers. As I mentioned earlier, in the parent function form, it's exactly 1 unit from left to right and 1 unit from bottom to top. That will again change once you start doing some stretching and shrinking. On the graphing calculator, if you want to investigate this, you have to press the math key. You have to right arrow over to the NUM option. Then you have to choose the int function. That is the greatest integer function. Here's the thing though, it's very hard on the graphing calculator to see where the open circles are and where the closed circles are. So if you're going to use the graphing calculator to help you, you do have to make sure that you know what it's supposed to look like. If you're not 100% sure, you can always check the table, because obviously anything that it gives you an error or undefined, then that's where the open circle has to be. A quick reminder about the rules for transformations. We're going to have a whole nother lesson on this upcoming, but this is just reminding you, how do you know if the graph is supposed to move up or down or left or right or stretch or shrink or do a reflection? So again, we're going to have a whole lesson reminding you of that, but you just need the basic ones for tonight. So here is one reminder for you using X's and C's. Here's another reminder for you using a slightly different notation and then showing you applications to the absolute value in particular. Again, the homework tonight, there's very few that actually require transformations, but I figured kind of good to bring it into the conversation early. Speaking of those transformations, so on the left side here, this is the parent function. So then let's say that instead of graphing the greatest integer function, I asked you to graph 3 times the greatest integer function. So that means that you would take each of the y values and vertically stretch it by 3. If you're vertically stretching a set of stairs by 3, it means that you have to take a higher step. So look, instead of stepping 1 unit from one step to the other, you now have to step 3 units from one step to the other. So that's where the transformation comes into play. You're essentially taking any step that's on the parent and just multiplying the y values by 3. So the x values don't change, even though the y values do. Notice that the steps still go from closed to open, and that should be the case unless there are any reflections. If I was going to ask you for the range of this function, it would not just be the integers, but it would actually only be the integers that were multiples of 3. So 0, 3, 6, 9. Again, there really is no nice way to say that in interval notation, so don't. Here, 1/2 x inside of the function. So again, here is the parent function. If there is a multiplier inside of a function, that is a horizontal stretch. So that means that instead of there being just 1 unit from the beginning of the step to the end, there is now 2 units from the beginning of the step to the end, because anything that happens inside is a horizontal stretch or shrink, and you always do the opposite. So this is a horizontal stretch of 2, which basically means you multiply every x value by 2. Again, notice that it's now still 1 unit up, and notice that it is still closed to open. Anytime I ask you to graph something with the greatest integer function, it really is just easier to kind of think about how it relates back to the original and then plot a couple of points as needed. So here in number 3, they're asking you to graph the negative greatest integer function. And again, if you remember your transformations, and if not, they're a couple slides ago, something on the outside is a reflection over the x-axis. So if you have the parent function in front of you, and you reflect it over the x-axis, anything that's on the x-axis is going to stay there. So there is a step that lives on the x-axis, and that's going to stay exactly where it is. Then again, try to envision what else is happening. So normally there would be a step above it. Instead of the step being above it at 1, it's now going to reflect down. So there is going to be a step here. Sorry, again, it's hard for me to draw open circles and closed circles on this. Here would be another step. Here would be another step. And then you'd also have a bunch going the other direction. So again, essentially you would take anything from the original function and simply reflect it over the x-axis. So you now have a set of stairs that you'd be walking down as opposed to walking up. And I don't need to see a couple of the stairs, no need to get crazy as long as I kind of get the main idea. Here in number 4, so again, transformation style, this would be an example of moving the staircase right 3 and down 1. Because there is no stretching or shrinking, once you move one of the steps, right 3 and down 1, you essentially would then just have to move all of them. So I always say, think back to the original step. The original step on the x-axis is from 0 to 1. If you are now moving that step 3 units to the right and 1 unit down, then you are going to have that step there from 3, -1 over to 4, -1. That's what happens to the step that originally is from 0 to 1. And then all of the other steps would move in the same fashion. So the next step would usually be from 1 to 2 at 1. If you were to move that 3 over and down 1, you would get your next step right here. And then the process would continue. And again, it's still going from closed to open. The only way that that changes is if you reflect it over the y-axis as opposed to the x-axis. And then you can graph the greatest integer function in conjunction with piecewise functions. So here we have a piecewise function of 3 pieces with a greatest integer function right there in the middle. So starting with piece number 1, x squared, if I plug in 2, I get 4. That's an open circle. Plug in 1, I get 1. Plug in 0, I get 0. -1, 1. And then again, you just need enough points that I can see what's actually happening. Again, piecewise functions are kind of nice to do in different colors. So the piece in the middle, you're doing the greatest integer function just from 2 to 4. So if you plug in 2, the greatest integer less than or equal to 2 is in fact 2, which is going to give you a nice closed circle. Then you're going to have a step between 2 and 3. Then if you actually plug in 3, you're going to get back 3. So that's going to give you another closed circle. And then 4 is the limit. You can't actually plug 4 in, which is why it remains as an open circle. So you only have 2 little steps as part of the greatest integer function, and they look exactly like that. Finally, for the third piece, that's the easiest one. That's just a constant function. So if you plug in 4, you're going to get back -3, and that's going to be the case, closed circle, and that's going to be the case for anything that you plug in. So that's just simply going to be looking like that. Domain, again, is all real numbers, as it generally will be. How about the range? So for the range, the lowest y value that I see is -3. And then there's actually a great big gap there. So -3 is kind of on its own. You're going to put it in a bracket to show that it's on its own. Then remember the U, the union, is what we use when there's a break to show 2 different intervals. Then the next y value that's defined is at the origin, 0, 0. So you're going to start at 0. And then it's going to keep getting higher and higher and higher all the way up to infinity. Finally, a couple of applications of these piecewise functions. So take a look at number 6 here. During Superstorm Lupinski, it rains over a period of 12 hours. It rains at 1 inch per hour for the first 4 hours, 2 inches per hour for the next 4, 1/2 inch per hour for the remainder of the storm. Create a piecewise function to represent the storm's rainfall and use it to evaluate it f of 7. So you are essentially trying to create a piecewise function. You can call that piecewise function whatever you want. So let's go ahead and call it f of x. Based on the information that it's given me here, it seems like we're going to need 3 different pieces. So it rains for a period of 12 hours. So 12 hours is going to be the maximum here. You're going to assume that time starts at 0 because you can't have negative time. So it rains at 1 inch per hour for the first 4 hours. So my first domain is going to start at 0. I'm going to use variable x, and it's going to end at 4. We're going to include the 0, and we're going to include the 4 because of the fact that it says the first 4 hours. Then it's going to be 2 inches for the next 4 hours. So that would be from hour 4 to hour 8. Don't include hour 4 because you've already included it in the previous step, but do include hour 8. Then it's going to rain 1/2 inch per hour for the remainder of the storm. So the remainder of the storm is from hour 8 to hour 12. Again, don't include the 8, but do include the 12. So right there, that is your ability to kind of find the different domains. In this case, they're all 4 hours, but that certainly does not have to be the case. So here's where it gets a little bit tricky. If you were trying to write a piecewise function like this, where each piece depends on what happens in the time before it, you're always going to have to refer back to the previous piece in order to write the appropriate equation. So it rains 1 inch per hour for the first 4 hours. So how do you write that as an equation? Well, 1 inch for hour 1, 2 inches after hour 2, 3, and 4. So all you do to set up that piece is you just need a variable x. So 0 hours would be 0. Then after 1 hour, there'd be 1 inch. After 2 hours, there'd be 2 inches, all the way up to 4 hours, under which there would be 4 inches. Then it gets a little bit trickier because it's going to rain 2 inches per hour for the next 4 hours, but you can't just write 2x. You have to include what happened during the first 4 hours. So I'm going to show you how to do this off to the side, and then we're going to simplify it and put it into our function. So when they say that it rains 2 inches per hour, they're only talking about the hours past hour 4. You've already included hours 0 through 4 in your first piece. So the way that you say only for the hours past hour 4 is you say x minus 4. Then you need to take into account what's the maximum amount of rain that already happened in the first piece. So the maximum amount of rain that already happened in the first piece, basically, where does the first function leave off? So the first function would leave off at time equals 4, which would mean that there were already 4 inches. Technically, you could leave that as your answer, but if you want to simplify, 2x minus 8 plus 4, and you would go ahead and simplify that to be 2x minus 4. So using that simplified version, you will now be able to, in one calculation, plug in 5 for hour 5 and find out exactly how much rain, 6 for hour 6 and find out exactly how much rain. For the last piece of the puzzle, it's 1/2 inch per hour for the remainder of the storm. So again, I'm going to do the work off to the side, and then we'll go ahead and add it back in. So here it's raining 1/2 inch per hour, but only for the hours we haven't already taken into account, which means anything over the first 8 hours. The first 8 hours was already taken care of in the first 2 pieces. Then, in order to find the number in the back, you have to find out where did the previous piece leave off. The previous piece always leaves off by plugging the maximum value into the equation. So 2 times 8 is 16, minus 4 is 12. This is going to give me 1/2 x minus 4 plus 12, which means that 1/2 x plus 8 is, in fact, the third piece of the puzzle. Now, again, you need to kind of break it up as such because you want to be able to just plug in a single number 9 and tell me exactly how many inches of rain there is. Yes, you could kind of make a table and write out each hour, but the whole point here is that we want one-stop shopping. Finally, the last thing they wanted was use it to evaluate f of 7. So f of 7 means at hour 7, exactly how much rain has fallen. So f of 7, you're going to plug that into the second piece. 2 times 7 is 14 minus 4, which means that there are exactly 10 inches of water that have fallen at hour number 7. So you're going to see more of these, but again, anytime you yourself have to take a word problem and write it as a piecewise function where each piece is kind of dependent on the previous piece, you always have to kind of take that into account. Last but not least, so this is an example of a word problem where I would not ask you to come up with the function because it's not something that would be easy for you to do. So the cost of a phone call between the US and China is 60 cents for the first minute and 42 cents for each additional minute or each portion of a minute. The fact that it's a portion of a minute is how we kind of have a clue that it's going to be a step function or the greatest integer function, because you're going to have a lot of values that are the same y value, and then ultimately they're going to jump up or jump down. So here is the equation for the total cost in dollars of a phone call for a certain number of minutes. And again, I would not expect you to create that equation. All you have to be able to do is answer some questions about it. So starting with sketch a graph of this model. So I'm going to go ahead and start by making a little table since I'm not really 100% sure what it's supposed to look like. Think about a phone call. You certainly would not have a negative call, so you're not going to include any of the negative values. Also, when it comes to 0 minutes, you're not going to have a call that's 0 minutes either, because then obviously you wouldn't pay anything for it. So let's kind of keep that in mind. So let's say that you're only on a call for a half a minute. If you plug a half in for t, 1 minus a half is a half. A half is going to go down to 0. 0 times 0.42, you're only paying 60 cents if you're on for 30 seconds. Let's say you're on for the full minute. If you plug a minute into that equation, turns out you're still just paying 60 cents. Once you're on it for a minute and a half, then if you plug that in, your bill jumps to $1.02. For the full 2 minutes, still $1.02. Once you pass the second minute and you get on towards the third minute, you're going to be paying $1.44, and basically it's going up 42 cents per minute. So how do you kind of make that? I'm only going to graph the first quadrant, again, because of the fact that you can only have positive time and you can only have positive money. So this is 0, and then I'm going to consider just the first 3 minutes, and then I'm going to make my steps as big as the y values that I found. So 60 cents, 102, and 144. As we already said, you're not going to be on the call for 0 minutes, but for anything over 0, up to and including 1, you're paying 60 cents. So you're actually going to have an open circle to start and a closed circle to end. Again, it's not something you can memorize. It's something that you have to just consider. You're not going to be on the phone for 0 minutes. If you're on the phone up to and including 1 minute, it's going to cost you 60 cents, which is why it's going from open to closed. When you jump to the next step, again, now you're going to be open and you're going to be ending closed, because anything between 1 and 2 minutes, that's going to cost $1.02. Then on to the third step. And again, this would now continue to infinity. Just showing me a couple of steps would really be more than sufficient. Finally, what is the cost of a call that lasts 12 minutes and 30 seconds? So 12 minutes and 30 seconds would, of course, be 12.5. You would plug that in for t. So C of 1.5 would be 0.6 minus 0.42. If you do 1 minus 12.5, you're going to get negative 11.5. The greatest integer less than or equal to negative 11.5 is negative 12. If you go ahead and plug that into your calculator, it's a good thing that it's a negative times a negative, since the company should not be paying you to make a phone call. Turns out that's going to cost you a total of $5.64. So this was a lesson on piecewise functions and the greatest integer function in particular. Again, feel free to go back and watch it as many times as you might require. And now you are in a position to go try homework number 7. So homework number 7, you're going to label it as such. Again, you're going to be doing your homeworks in a paper notebook, and you're eventually going to be turning in all of your homeworks to date by the time that we get to the first test. Okay, the answer key to homework 7 will also be posted. So as you do the problems, check the answers, make note of problems that you still have outstanding questions on, and we will address those during class whenever we have a chance. Okay, so thanks guys for tuning in, and we will catch you next time.